So, where were we? And it's okay if we'll be a little behind. I'll just keep talking tomorrow about these topics. And then, like we said, this week we're talking about text, like document processing, where text is your data source. And that's meant to be today, but it can continue tomorrow. And then the lecture 7B is supposed to be on support vector machines and a completely different, like another classification model. So they're kind of two separate topics this week. So if we don't start SVMs till next week, that's still kind of okay. So let's talk about text. Oh no, let's talk about streaming data. We have to finish this, that's right. So the last time I was there, when we were having lectures, we were still talking about ensemble methods for streaming data, and I described this Hoeffding tree, right? So this is a regression tree approach where we can take in new data as we're going, which was the main problem with one of the drawbacks of random forests and things, that they can't actually deal with changes in the data, because you have to train all the data batch up front, and then you get your model, because you're trying to optimize in the decision tree to determine those splits in a really efficient way, right? So this Hoeffding tree used this approach from statistics, which helps you build confidence bounds. So if you're looking up things about try to write bigger. Confidence bounds is another place you'd find out all about these kinds of methods. And the idea is you're trying to come up with a probability of, like, once you learn something, how accurate, how confident can you be in it, right? And the Hoeffding bound is one of these that tells you how close you should expect to be to the true mean of a variable given some samples of data. So how many samples you would need for that to be a good estimate, right? Right, so you get an estimate here that says with probability 1 minus delta, and delta could be something like, 1%, so probability of 99%. Our estimator is kind of within epsilon of the true estimator given these variables, right? And R is, the range of the variable, right? So your variable X is in some range. If it's in 0, 1, then that's just what that is. You have that, and then N is your observation. So how many data points, how many samples you have, right? So we can get this, how close we can be with a certain probability range. So that, as we talked about, there's a whole algorithm, essentially builds a tree using that Hoeffding bound, and it basically says, don't expand the tree unless you're going to be sure enough, right? And so in Hoeffding tree, when you get to some leaf, when you're building it, and you're here now, you have to decide, should we split or not, right? And it uses this this bound to decide if you should split. You've already said ahead of time you want to be, you give it as input, right? So parameters that you give this algorithm include the delta that you basically want, and I think even the epsilon, right? So you tell it you want to be 99% correct, and you don't want to have more than 2% error or something. And then once you've reached that threshold, then it does some various things to decide if they should split or not, right? And then split. So you only split when you need it, when you can do it safely, in the sense that every leaf now in your tree has this high enough confidence, right? And so you wouldn't split if it's going to be less data points than that. So it means that every leaf has quite a lot of data points in it because it's got enough statistical significance. So another method that does this approach, but in a very different way, is Mondrian trees based on Mondrian processes. I really like these. We've done some papers on something using these. We didn't invent these. Somebody, very smart people at U of T actually, and the famous Eli Tay, who's like involved in a lot of stuff in reinforcement learning and deep networks that you'd seen famous papers on. They kind of worked on this. And so they're building trees, but doing it in a different way. And it's called Mondrian Tree because it's this artist, is French, I think he's French, maybe Belgian, artist called Pierre Mondrian. And he made a bunch of modern art, right? So he doesn't paint pictures of dogs and cats and angels and people. He did geometric figures. And he has a series of paintings like this. It's kind of one of the nicest looking ones that I like. And so this kind of pattern is called a Mondrian pattern, right? So it's just, you can get, you know, kitchen tiles in this pattern or book covers. There's all kinds of things. It's just kind of neat geometric sequence. He was experimenting with color and lines, but they took inspiration from this to say, what if we built trees this way, right? We said when we're learning a decision tree, right, that essentially we're dividing up the space, right? So if you think about that, if we just had a binary space and we're you know, dividing on x and y, and then we said that x, you know, is greater than 5 is what this split was, then basically, you know, when you're at 5, the first split is here, right? And so all the data points on this side of the thing are here, and all the data points are there. And this would be a perfect situation for a different color marker. But it doesn't matter. Right, and then the next split might be on y. Sorry, let's have that. Ah, sometimes click means next. You might have y on the second feature might be y less than 1, right? And then so you'd have y equals 1, and so you'd have a split here. And you keep drawing rectangles, right? So in the end, once you've built a decision tree, you've essentially drawn rectangles over a whole space. But importantly, when you're doing a decision tree, you just have x greater than 5, and that really means anything in that feature that's greater than 5 goes on one side, and anything less goes on the other side, right? All the way to infinity, right? So if this feature goes on forever, or to some maximum or minimum numbers, it's all of the points in that direction. So you do a split, and you commit to all the points on either side. In Mondrian Forest, we're saying, they say basically, why commit? You're making a split because you want to distinguish two sets of points, and there'll be another slide after that has a bit more ideas on this. Sorry, this is messy. So let's say x points are one type of data and dots are another, and so they're split in various ways. And so when you come up with a split and say, okay, let's get all the ones on this side, why are you committing to infinity in this direction? You should just only commit to what you saw, right? And so the Mondrian Forest basically is more cautious. When it creates a split, it only commits to the data it sees currently. And so that means later on, if you see another data point outside here, then you haven't committed to where it should be. I'm saying new here. When new data arrives, you haven't committed to where it should go, and so you have more flexibility on whether that should be in the same block or not. That's the main idea. So the way they do this is they come up with an idea of a split time. So not only are you going down depth in the tree and features, you're saying what's the kind of time since arrival, right? So this is kind of like arrival time of a data point. Kind of, it's not strictly that, but you could use it that way. If your data is arriving in time, then the longer it takes, maybe the more likely it is to be a different data point, right? And so as time increases, data points are going to be deeper in the tree, so we're using time instead of depth here. But then the increase in time, yeah, so in terms of rather than just saying we're going to go down and now new data points arrive at level, you know, so we begin at level 1 and now we're at level 2, There must be a way. There isn't a way. It's weird. Ugh. Okay. Instead of just saying that every time we split the tree, the depth gets higher, every time we get new data points, we decide has enough time passed. And we kind of randomly sample from an exponential distribution, which kind of has a nice representation of time. So these distributions are useful for processes that are kind of having data points arrive over time and trying to say it has enough data arrived to be significant. And so based on how much data you have currently, so a very large block of the tree, you maybe want to wait a little longer before you have enough data to make it significant enough to split it. And then once that time has been sampled to be above some threshold, you say, okay, let's split. Let's go down in depth, right? And yeah, so the time is 0 for the root and infinity for the leaves. I forget what that means. There's a bunch of papers on this. So the way it looks then, you're still building a decision tree in the same way. So at the end, you'll have a tree. And usually what we're doing is forests. So we're not going to have just one tree. We'll kind of use the random forest idea and build many of these. But each individual tree is still a decision tree. It's got some feature and a split point. And here they're indicating very nice shapes for each of the spots. And like I said, when you come up with a split, you're building a box around those points to say, okay, I've split on x1 at this level. So this one was at 0.37 and x2 here is at 0.5. So I've got this split like a normal decision tree, but I've only committed to this, right? So if a new data point arrives in here, I don't know where it would be, right? It wouldn't necessarily be in this block. It could be in any of them, right? So you have to decide where to place it and how the split will work. Right, so you're just finding an entire rectangle. So basically we have to store more parameters. So every split point now has a min and a max. And the min and the max are defined on the current data that exists, right? So your model is always adapting to the data that it has actually seen. Right, so that means they're perfect for when new data arrives for basically updating the model easily. In the original definition of this, it was defined for doing regression or classification. So that's how they were used. And we have a paper where we use this for when I talk about anomaly detection in a few weeks. You can also use it for that. That's our own algorithm from my lab, but it relates to some of the stuff we talked about with trees. So we'll talk about extremely randomized trees and the way to do anomaly detection with trees, which is a bit different and more focused than these, right? Because so for regression and classification, right, once you build your tree, you want this thing to be a nice, representative sample that you can make a prediction with, right? And so you could fit some model here, or you could just do logistic regression, or just do majority count and tell me what class they're all in, or predict the average. So you could predict the mean of these data points, or you could fit a curve to it or something. But for anomaly detection, you kind of want to do something a bit different because you want to know, is this data point normal or strange? And so it's a different question that you're kind of answering. But again, we'll talk about that, I guess, next week, because that'd be unsupervised learning. So Mondrian processes themselves are interesting models to look at as like probabilistic models of integrating, like making predictions about data according to some distribution that's based on that only the input data, and which is more cautious. So it allows streaming and maintains a probability the entire time. Technically, they're an infinite probabilistic process, so they can handle any number of features. That's another way of kind of saying that they're non-parametric. Remember we talked about parametric versus non-parametric before, I think we did. That, you keep adding more parameters that as the data goes up, right? And that's what decision trees are in general, right? more data means more parameters. And so your model can keep fitting and improving. But they do it in a continuous probabilistic space, and the math is quite complicated, but they're very useful for various things. This tree-based one is kind of the most directly useful. So in terms of the algorithm, a bit more detail, what does it do? Yeah, so it tries to figure out whether that data point is in that block or not. And if it's already in the block, it just adds it, right? So since it's got this approach, if I said there's new data points outside, but if you get a new data point in here, you just say, okay, it's one of these. I'll add it to this model and update that, and I update the probability of this block, and it works fine. So it can just stop somewhere, or it can decide to add it somewhere else. So this is just a bit more detail about the algorithm that I was describing before. So it's about deciding whether you should split or not based on this time, and the time is going to be something you sample randomly, right? So you're sampling from this distribution, and if the sample that comes out of that is high enough, then you decide to split. And then you have to figure out where in the tree this new data point should arrive, right? Okay, I'm still repeating some of the things I said earlier, because I remember having it on a slide, but I just said it. So it's just that it can be used on other methods. Let me see what else I had. Okay, that's it. Yeah. Yeah. So I guess the advantage, the other place then is that when you're if there's enough new data points out here that arrive, because it could be done in a batch way. So the code for it allows you to have batch points. So you can get 1,000 new points, and maybe they're in all these different spots, and now you've noticed, oh, there really are enough of them that they're outside here, and so you could basically add a new rectangle here, and it would actually insert it, in the middle of the tree somewhere. So it does a little bit of reorganization and says, this one now has a parent, and we'll have a new child over here which has these data points, because that's a better fit. But it doesn't have to restructure the whole tree. It's just because it hasn't committed to the new data points yet. It only uses the space outside those rectangles to decide if it should add it. So it's another creative way to do it. There you go. I answered your question. So it's a good question. Gave answer to question. I hadn't seen the post, and it already just happened automatically. That means you're predicting what's going to come next. What's the important thing? So that's good. Yeah, it doesn't exactly do the Hoeffding tree test so explicitly, but you set some threshold and say, we're sampling from an exponential distribution every time your points come, and if we get a sample from that's above some value, this threshold, then that means we're going to split. And choosing that value, you can use the Hoeffding bound to say, if you do 1,000 samples from an exponential distribution and it's above 95, how much data would you need? How confident would you be about that, right? So you can use the same idea to that. There's other bounds other than Hoeffding that have different properties. That's one of the most stable, useful ones people use in this field, but there's a whole area there if you're interested in streaming data or you need it for your research. I can help point you to more things because that is a whole field. And actually we'll even have, on a related point, just realized, I used to, this is the last one I'm running, but I used to run, this is related, there's a talk coming in a couple weeks from the Waterloo Ai Institute, which anyone on campus doing AI is a part of. If you're a grad student and you're interested in AI, you can contact them and get added to their mailing list. I assume they have a link here for how students can get added. Oh, that's external. So this is the institute on campus that kind of unifies all the different AI research. It's pretty new, so we're kind of just, it's only been getting started the last couple of years. There is a grad association, so if you're interested, you can, at the very least, email some of these people, or you can just ask me. One of my students is, or was at least, president of it until, I think she's still president. So it's cool. Basically, we just have talks at this point, and there's some funding events. But on March 9th, so after lecture on that week, so after 9B. My old supervisor from my postdoc, Tom Dietrich, will be coming giving a talk, and he's like a master of some of these decision tree methods. He also does stuff for planning and like reinforcement learning and MTP planning. So that's what he's going to be talking about. But he's been big on performance guarantees. So when I was doing postdoc with him, we were doing research on some of these tree-like things with Hoeffding bounds because we're trying to find ways to use trees for prediction and especially for planning in ways that gives you guarantees, which is really hard to get guarantees because you need so much data. So he's going to give a talk on what he's learned recently about that. He always gives really good talks, and he's very influential and connected. So it'll be a good talk, which you can watch on, like, to be a Teams live stream here or somewhere. I'll have to email them to update that link sometime soon. So you should listen to his talk. Everything he's talking about, well, some of it will make sense, especially these performance things we're talking about. The other things, the MDPs, you'd have to take my undergrad course on reinforcement learning, but they're not that complicated. If you do anything with planning, you might know about it already. So yeah, that's just a ad for something related to class. Great. I guess any questions on anything about decision trees or streaming, any of that stuff? So I'll never talk about trees again. No, that's not true. I love talking about trees. And they're kind of, these days, that's the end of my decision tree topic in general now. I think they're underappreciated, decision trees in random forest these days, because deep learning is so exciting and powerful. And deep learning is, in a way, more flexible. So it's being used for a lot of things, but it needs a lot more data to do the same thing that a tree can do. It may actually be more powerful in some way, but if your data is not super complicated, often a tree-based approach might do just as well and be more efficient and compact to learn. And like we're seeing a bit in the assignment, the parameters kind of make sense a bit, even if there's many thousands of trees, well, hundreds of trees, you know what each one is, right? So the parameters all have a kind of a story you can connect to, so it helps you tune them. Neural networks, this has not been the case, so it's taken longer for people to get them to work. Like decision trees and random forests were, defined in the late 80s and 90s and used immediately and super powerful and effective for everybody right away. Neural networks were defined around the same time and only got popular really in the last 10 years. They were popular for a while, and then everyone found they weren't that useful because they didn't know how to work them, right? So I think they're underappreciated, and they're mathematically they're equally as powerful as neural networks. It's just that somehow neural networks work better for if you have a lot of data, then they can actually do better, it seems. See if we have any questions.
Professor?
Yeah, go ahead.
I was curious, so like for the Mondrian forest, how do you kind of make it more robust against like outliers, or how do you kind of set a threshold for so it doesn't, like if you think that you're going to have, say 10% outliers, how do you kind of make it so that it tries to ignore those nugs and not start partitioning points that might come in that are incorrect technically?
Outliers. So what would be the effect on outliers? For some reason I can't get to every slide. Okay, here we go. I'm trying to think if they're really any different in terms of outliers than random forests or other things. They inherently are better, I guess, for outliers, right? Because if you think about an outlier, really, right, would be some data point out here that we've never seen before, but literally the axis assume this isn't a max of 1. We've got some feature and it goes on further. We've just never seen data points this high. So we've got a data point now way up here. I'm pretty sure this is noise or something weird, and we don't want it to just be in this class. So Mondrian Forest doesn't automatically put it in there, right? It would say, okay, we got some new data point, and you try to figure out where to put it. Usually it's used in batch mode. Go ahead.
But that assumes that it's at, I was going to say that assumes that it's like, say outside, some really large bounds, right? But like here, you have like the 2 green stars, right?
Yeah.
Well, how do you know those green stars are like those green stars could just be like, I don't know, weird outliers that just kind of popped up there, but maybe actually that whole side, that whole right side is supposed to be blue squares. But you
Oh,
have
okay.
stars there now, and now it's going to start thinking that you have green stars there.
Yeah, no, that's true. I mean, that can happen in any model. But I mean, hopefully, if that's true, then later on you're going to get more data, right? That undermines that, right? And so these features would show up in the same space, and then you'd realize that actually this area has more blue boxes, and it should be all these, right? So the label for this.
Does it just ignore those then?
No, well, it would ignore them. They'd still be in the data set, right? Because basically what you've got here is you've got this. So the picture here doesn't necessarily indicate that this label, this leaf, only contains stars. It's just, I guess, saying that's what the category is. Do they have a description of what they're meaning here? But I mean, in general, the leaf could have mixed data, right? So it could have, some number of stars, some number of squares, some number of circles, but the most it had was stars, right? So it's not a pure, what we call pure, right, where the leaf has only one type of data point. So there's no decision here that you have to stop. So when each of these nodes is pure, their diagram's a bit simple that way. So it really could be just a mixture. It's just that the circles are probably the dominant one in here. So yeah, if it starts becoming that you get more and more data points, then this would start becoming, this would change to be a square label, right? So if we're saying that the label that we've picked for each leaf is that originally, then we'd say if we get more data, then now it's going to become square, just because the data points are in that range. So that would happen automatically. That's why you want lots of data, because outliers will get washed out in lots of data. A bigger problem is if you do get a data point that's way outside in terms of feature space, then how do you fit it? So how do you draw a box around that and say this is reasonable? And if there aren't that many data points around it, that's just a hard problem in general. So maybe in your pre-processing, you could still just get rid of this, right? And say it's an outlier, I'm not even going to use it yet until I get lots of data points in that area. But at least in Mondrian Forest, when it gets it, it wouldn't put it in the same box as other points. It would define a new box for it. But I'm not sure how it works in terms of the algorithm. If you only get a couple points, how do they define that space? At some point, they'd have to just commit. So, yeah. Am I on slide 42? I am. So Jason has a question. Is the space outside the gray squares the space that can be allocated to either expanding or creating new groups? Yes. I'm hesitating on expanding because I don't remember if the algorithm allows. Oh, I don't have the Mondrian Forest algorithm up here. I should. It to just actually change the variable and expand it. Yeah, I have to go back and look at the algorithm and see. So definitely it's the place when new data points can arrive. So any place outside the current blocks, you can make new splits and add them there as this tree. I don't know if it changes after the fact. I forget. We have to go check that. Can existing splits be changed? That's a good question. But it's definitely for the ones outside. And remember, this is just a two-dimensional representation. In reality, your data has like 100 dimensions or 1,000 dimensions. And so there's really, it's not just like an area that's everything inside the block or all the data points in the tree. It's a weird cubist Mondrian painting in that many dimensions of various regions in space that all have defined rectangles with points in them, and then lots of empty space in between. So it looked like a map of like galaxies or something, right? Where there's these squares around each of the galaxies, and places outside the squares are places we've never seen any data, and so we're not committing to what structure in the tree it is in. But once you see some data points, you'll have to find a way to get to that spot in the tree, right? And so you have to connect each galaxy once you find it in the 3D, whatever, ND diagram. So it's not as simple as just what's inside or outside the box. This box is a complex high-dimensional structure, but it's defined with greater than, less than splits, so they're all rectangles or prisms or whatever. Great. Any other questions about trees? Performance, I don't have exact numbers on the performance for it. If you look up the Mondrian forest papers, they have comparisons. They're faster than Hoeffding trees because they don't do as much recalculation along the way. They're always maintaining these probabilities in these sets, so it's more efficient to add new data points than on previous ones. That was the reason they came up with this, that it's a very well-defined probabilistic meaning, but you don't have to compute these Hoeffding bounds constantly because you're just sampling from the exponential, and then if that sample goes above t, then you make a new split. So that's much simpler to compute than these Hoeffding bounds all the time for all the data points. So they made it's much faster that way, but it still has a theory behind it that lets you say what's the probability of this label being correct, right? So yeah, they're faster than that. They're slower than like random forests directly because you have to, they use more memory because you have to store these extra information for distributions and counts and like upper and lower bounds, and you're doing a bit of more calculation on every split, but not as much as other things. So that's been one of the challenges of trying to make decision trees based systems streaming, is that the proper way to do it would be to, like, when you get new data points, go back up the tree, figure out what the best split would be, and recalculate a lot of it, or rotate the tree. And all of those calculations get really computationally expensive. And so Mondrian Forest was trying to be one where when you get new data points, you can just basically run down the tree, find the right spot, and add it, but still get a probability out. So it's probably as fast as it could be under this kind of formulation. How do you pre-process streaming data? That's a good question. Yeah, so I was saying, throw out outliers. If your data is streaming and a lot of it's arriving all the time, obviously it's going to be harder to do that. So I just meant in general, you could pre-process by like getting rid of data points that you know are outliers or seem to be suspicious. But yeah, as the data is arriving, you may not have that much time to do it. You can still pre-process. Like the usual assumption is that they're arriving in batches, right? And so you get your data keeps arriving, and maybe the initial training of this thing is on batch 1, and then at some point later you get another batch, and that data has a significant amount in it. So you could still pre-process each batch and say let's do some pre-processing on this data, remove outliers, fix holes in the data, and then feed it to the tree. But this could be another 10,000 data points, right? And that would help with some of these issues too, because you'd never get one point somewhere, you'd get a new bunch. So it's not usually done where you say, okay, give me one more data point and I'll add it. Now give me another one data point, because that would be hard to pre-process because you don't know anything about a single data point, and it'd be kind of inefficient. So you're usually saying these batches, and they're probably fairly large batches. But yeah, streaming data is fundamentally harder to do this because if there's way too much data at some point, you just have to throw it in there and see what happens, or throw some of it out because you can't store it all. If you have very large, high throughput data, and like I was saying, Shailja knows a lot about this from her research in one of the other labs in ECE, they deal with very large streaming data all the time. And so you want to learn a model in some way, but you can't store all of it. And if you just even wrote all of it to disk, it'd be terabytes. So you basically have to delete some of it. So you come up with some way to sample this and come up with a good, representation of it, but then just throw it into the model and then delete it because you're never going to be able to go back. So a lot of these things we do with data when we have time to pre-process it may not be possible with streaming when you have a lot of data. It's just harder. yeah, you could put some kind of heuristics to say, data points have to be in this range of values, or we know something about the data. So if you're getting sensor readings from your car and you have various different heat and pressure sensors and stuff like that, there's ranges that are not acceptable or strange, and so you have limits that say, certain data points maybe we're gonna stop the system or do something else when we see it, right? Anything you can do with that will help. Hemon asks about validation accuracy. We're talking a lot about, train, test, validate, deciding your data up and tuning your algorithm. That's harder to do when you're streaming, but you're not designing the system anymore at that point. So your validation approach is really to help you design the algorithm and say, what should the settings be? So Mondrian Forest, we have a couple more parameters. We have to say what probability and threshold we want. We still have to say how many trees we want to grow and how deep we want the trees to be, maybe, although that's handled a bit with the time. So you'd still want to do some kind of preliminary experiments on whatever data you have, and you create a validation set for that to figure it out. But once you get something running in the real world, you're not having a validation set or anything. You're just running it, and you try to do testing in any way you can if you have true labels. So I guess in the full domain where it's deployed and it's getting new data all the time, you don't have to worry about this validation accuracy thing because you're not constantly changing the way the model works. But when you're designing it initially, you can still do that. So if you do all your design in batch, somebody gives you data ahead of time, and then you pretend it's streaming by feeding it batches in a row, you could still do it that way. And you could have a validation set as a subset of one of these batches and say, okay, now I'm going to decide how many trees it should be, and that seemed to work. And then once I've picked the number of trees and the probability threshold, then I train it on my test data going forward. But then you're not using your validation anymore. Great. Yeah, so some other people have other suggestions you could have. Depending on your system, this is where domain knowledge for your system comes in really useful. What is reasonable in your data, and how do you put some rules on it to say, oh, this would be an impossible value or a very unlikely value. You have to be careful because the more of that knowledge you put in, the more you're biasing the model. But that's sometimes what you want, right? To make a fully safe, fast, robust system, you probably have to put a lot of human knowledge into it. So like we do stuff with cars, you don't want to just say, oh, let's learn from scratch and let the data decide what the right way for running this car is and driving autonomously, because you're never going to get enough data to see the full world. So you want to put all kinds of rules in to say, this is what's safe. Never go this fast. Never go this slow on the 401. Never change lanes this quickly. Whatever your system is, you definitely want to put in rules that say, here's the bounds that's reasonable and safe, and then you train within it. But in a pure machine learning research sense, we often want to do what's called end-to-end training, where it starts from scratch with no knowledge and a bare model and the data, and then it learns the best fit for that. And that's very fine for like labeling images with dogs and cats and people and boats in them, or face recognition, or financial fraud or something. You don't necessarily understand the problem well enough, and you know the right answer, right? But in a lot of domains, especially where safety or performance are important, you want to put your knowledge in to make sure that it doesn't kill anyone when it's running based on some uncertainty, right? Because these models, again, right, we're talking about probabilities, right? What's the probability of some point being in here or not? If you have the Hoeffding bound, you've got, a 99% chance of having a 2% error, but that's still a lot if there's a lot of samples or you're running it for a very long time, right? Or with your COVID diagnosis things, you could have a model that's 99% accurate. That means it's still going to get it wrong for thousands of people a year and kill how many hundreds of people, right? So that may not be acceptable, right? So you have to put in rules to say, just don't do this because we know these certain things are just wrong, right? Or incorrect. So there's a bit of a tension there about using domain knowledge and doing end-to-end training without any bias. And some communities are very focused on end-to-end, but as engineers, I would think that's actually often not the case. You want to put in the important assumptions so that your system is safe and works, but you have to justify each of those, right? Why did you have this assumption? What is it useful for? Great. Okay, so let's end that part, and I will start my next topic. But it's kind of its own big topic, so I'll just get some of the introduction stuff, and then we'll continue talking about this tomorrow.